Welcome to NPTEL. Myself Dr. Jayanto Das from Department of Metallurgical and Materials Engineering, IIT Kharagpur. I will be teaching you advanced materials and processes. Today we will discuss about the soft magnetic materials. Last couple of classes we have discussed elaborately about the fundamentals of magnetism and the hard magnetic materials. Also we have discussed how to improve the hard magnetic properties, means high corrosivity of hard magnet, and to make it much larger and larger with a large value of remanence magnetization or MR. In case of soft magnetic materials, it is just the opposite side, means we need low corrosivity, means the spin should be easy to align. Okay. So, this is a typical characteristic of soft magnetic material, and the development goes towards to make a material more and more softer. So, there are very important selection criteria for the development. So, couple of technical consideration are involved with. So, the first consideration is that the material should have high permeability. A permeability term means that is expressed by mu, that is B, okay, magnetization by the applied field, which is equal to 1 plus xi, that is the susceptibility. So, the permeability of a material, that is a material parameter that describes the flux density, that is the B, inside a material, in a magnetic material at an applied field of H, and a high flux density can be produced in a high permeability material at a very low applied field. That is a typical characteristic that we need for developing soft magnetic material. Now, on the other hand, we also need a low hysteresis loss, means I have a BH curve. So, where this is the H applied field and I have B here. So, if you look at such kind of hysteresis curve, then the net area under this curve is a circular integral of m into dB, that basically gives us the WH. WH is the hysteresis loss. So, this loss should be as low as possible. So, this loss can be only low when the Hc will be very close to the axis. So, Hc value should be very low. We already know that for a soft magnetic material it is less than 10 to the power 3 ampere per meter. And why we need a low hysteresis loss? Because the energy consumption will be less. So, let us say if I have to develop a transformer core, then we have to reduce both the eddy current loss as well as the hysteresis loss, and because of that we have to develop a soft magnetic materials. So, here also two other important aspect should be present, that is the large saturation or MS or BS value and the remanence magnetization. So, these two should be very high, means what I want to mean, again I show you with a hysteresis curve. When we magnetize a magnet, then this is the value. Here I have basically the applied field, that is H, and here is the M or B. So, applied field versus the magnetization. So, this is the value, highest value where the magnetization saturate, that is called as a saturation magnetization, and after withdrawal of the magnetic field, here at 0 applied field there are some remanence magnetization appear, that value should be also very high. So, this is a typical soft magnetic material characteristic. And also if we have to apply the material at higher temperature, also during application in a transformer core there is a temperature that goes higher, right. So, that is why we need coolant in a transformer. So, in that case the Tc means the Curie temperature from a ferromagnetic to a paramagnetic transition, that should be as high as possible, and that is one of the very important aspect of a magnet. So, for elevated temperature application, the Tc should be higher and higher. So, now let us have a look at the chronological developments and how many different alloy has been developed along this direction. So, here this is the Bs. So, Bs is the same as the saturation, magnetization or Ms. So, I am talking about let us say where it has saturated this one, and mu here, that is the permeability value. So, in that case we need to optimize both, that is the aim of the technical consideration. If you have a look, the typical silicon steel that are used for transformer core and let us say for iron cobalt alloy, they has a very high saturation magnetization. Okay. Now, ferrites are lying here, they are not so interesting in both the properties, okay. Whereas, the amorphous alloys are very interesting in case of the high permeability value, means we can generate more flux inside a amorphous magnet. So, the derivative of this amorphous magnet it was the met glass. So, the derivative of that is a fine met which has iron, silicon, boron, niobium and copper in the alloy. So that the composition can be vitrified, because we also need to consider that the glass forming ability should be higher, so that it can be vitrified, which we have discussed elaborately in the first weeks of the lectures. And then this fine met was developed. After with that the new series of this kind of amorphous and nanocrystalline magnets has been developed, that is called Nano Perm. Okay. So, they have a very optimized property in terms of both mu as well as the Bs value. So, here you see that boron and copper are present, here also boron and copper are present, but there is some other refractory metals has been added. And furthermore, it has continued and derived another new set of heat perm alloy. Heat perm has a very high saturation magnetization values, and in this case instead of iron it is iron cobalt. So, definitely adding another atom, there must be some exchange coupling between these two atoms like iron and cobalt. So, there are some benefit of that. So, so there is a chronological order of this development of this series of alloy that are lying here with a optimized value of Bs and mu. And this is a very interesting topic of our discussion, and let us try to look at for this developmental issue, what are the other consideration involved in terms of choosing the composition of an alloy. So, in case of a composition selection, we first need to consider some ferromagnetic material or the element. So, ferromagnetic materials means here iron, cobalt and nickel. These are the three important metals that has ferromagnetic in nature, and that contribute the ferromagnetic moment as well as to perform the spin alignment of the transition element. So, we can choose iron, one of them, which is one of the very important and cheap element rather, and then we have some other metal or metalloid systems. Okay. And here is some metalloid system which has tuning the magnetic and structural transition temperature. So, in case of metalloid system, we can choose let us say boron or silicon, these are very important. And now, in case of transition metals like M, here the transition metals are zirconium or niobium that are added. You have seen for these fine met and heat perm alloy series, there is some addition of that, and on the other hand there are some late transition metals are also added. So, in that case it has the slowest diffusive elements. So, copper, silver, gold, they are added in a very less concentration, but it basically assists. So, these two different type of metal that assist the retardation of the crystal growth, because we also do not like, if we produce some nanocrystalline microstructure, there should not be any grain growth. So, that is very much important, as well as it helps in partitioning. So, hybridization of 3D shell electrons with ferromagnetic to form or antibonding coupling above the Fermi level. So, these are some important aspect. Also, the enthalpy of mixing with iron with all these elements, that should be less. If we consider iron as a base element, which has a concentration level of 66 to 91%. So, this is a very common trend of development for the composition selection or of the alloy development. And now, by choosing some different electron pairs, we think about, let us say, the Bohr magnetron values with the electron concentration. So, this is a typical Slaughter-Pauling curve, which says that I may have iron vanadium, means I can choose here vanadium and iron. Okay. Then where it will lie. Okay. So, whether it is going to increase or decrease, but the interesting point here, that if we choose iron and cobalt. So, iron and cobalt together to be present, you can see that I can reach to a maximum value of the Bohr magnetron. So, Bohr magnetron is basically means that the single electron that basically spin around in its own axis, and that basically called as a Bohr magnetron. So, this Bohr magnetron value reaches to a very high level when we can couple these iron and cobalt together. On the other hand, there are many other element. In case of nickel base, nickel and other element pair, they are all lying somewhere here. So, in case of iron nickel, it is still better. So, this iron cobalt and iron nickel is a good pair of element to choose to achieve basically the highest value of the Bohr magnetron. So, so there are this is one of the very important design criteria for the alloy development. Now, let us compare between a amorphous material, nanocrystalline material or nanoparticle. So, if we consider a single nanoparticle, then the magnetization versus applied field curve will appear as a green color curve that I shown you here. So, this is a typical nanoparticle. A nanoparticle has some value, a higher value of Hc, as well as it has some higher value of your Mr, that is the remanence magnetization. Whereas, in case of amorphous material, that is presented in this that has the highest magnetic flux that can be achieved, and so we will get a very soft magnetic material. However, if we can couple these nanoparticle and amorphous together, then we can produce some nanocrystalline alloy, and that will have some optimized properties. Okay. So, this is the aim of the development. Now, here again we think about microstructure design by combining a soft amorphous matrix and a hard nanocrystalline phase, and that is a desired microstructure to achieve a good exchange coupling between the magnetic nanograins through the amorphous matrix. So, if you look at these three major series of alloys like fine mat, nano perm and heat perm, which has been developed chronologically. So, the heat perm is one of the latest series. Here we have iron silicon and boron, niobium and copper. So, in the phase we have alpha iron silicon phase, which is the nanoparticle or nanocrystalline grain that is embedded in a matrix of amorphous phase. The saturation magnetization is around 1 to 1.2 Tesla, which is quite high, as well as the Tc, that is the Curie temperature, that is less than 770 degree centigrade. But with the development, if we the silicon and let us say the niobium and simply add zirconium into it, then we get again that alpha iron, that is the basic design consideration of the microstructure, but we can achieve a higher value of the saturation magnetization of 1.5 Tesla to 1.8 Tesla, and the temperature is also increased. The temperature means the Curie temperature, means the material could be used at a higher temperature. Whereas heat from alloy, here the iron cobalt both are 44 means equal stoichiometry, and zirconium is again present and boron is present, copper is also present as the nano perm alloy. So, only the difference between nano perm and heat perm, that I am substituting 50% of the iron by cobalt. In that case, I have again iron cobalt alpha phase, which allow a much higher saturation value, because we achieve a higher value of the Bohr magnetron, and the temperature of use could reach up to 900 degree centigrade or higher than that, and that is the biggest achievement so far. So, the same value for the comparison of soft magnetic material and saturation magnetization, which could be MS or JS, any of the so, for the iron silicon, it has a higher corrosivity value and a higher saturation value, where the nickel manganese zinc or nickel zinc ferrite, that has a very low saturation value. Whereas the amorphous material and nanocrystalline material, that basically occupy a space with a relatively higher corrosivity. So, our aim is to go into this side. So, the corrosivity should be less, whereas a higher saturation polarization should be there. So, this is the 10 to the power 3 ampere per meter. So, this is the limit of the soft magnetic materials actually. So, cobalt iron has a very high saturation polarization and the very high corrosivity value. So, the aim of the development is this side, where the amorphous based alloys with nanocrystalline phase inside is one of the very important soft magnetic material with these 3 series of fine met, nano perm and heat perm alloys. So, the first we will start with the fine met series of alloy. Fine met is a trade name. So, like iron, silicon and boron present, niobium and copper. A typical composition of these fine met is 73.5 iron, silicon is 13%, boron is 9, copper is only 1. Now, is there any link with these other element addition? Only the glass forming ability is important, or there is any role of these other alloying element? We will see. So, first a quench microstructure that has a amorphous phase present is prepared in case of such fine met alloy. Then we anneal it and we basically get some copper clusters into it. These copper clusters actually help for the formation of iron silicon BCC alpha iron phase, that is the alpha iron, that is a BCC phase that assist in this crystallization process. Now, they grow with a suitable annealing treatment. So, your alpha iron with silicon, with some amount of silicon, they basically grow and they assist to develop of this nanocrystalline microstructure. A typical microstructure is shown here. You can see these are the same BCC iron silicon grains, which is alpha iron grains are present in a amorphous matrix. So, the highest permeability or mu value that results from the silicon content of the BCC nanocrystalline phase with a low magneto restriction. So, not only we should achieve a higher permeability, but when we produce a very high flux, it also changes the dimension of the magnet. I am talking about the physical dimension of a magnet can be changed, and this is a property called as magneto restriction. So, in case of magneto restriction, the dimensional change will occur in a ferromagnetic material upon application of a magnetic field. So, magnetic flux density as it increases, the dimensional change will also occur higher and higher amount, and that is not allowed, that is not desired property. So, this silicon content is important to decrease these dimensional changes in a fine met series of alloys. So, here you see that the size scale is something like 20 nanometer size grain present in a iron, silicon, boron, niobium, copper fine met series of alloys. Now, the Nano Perm is the second that is also derived, which is also a trade name. In this particular series of alloys, we have iron, I have a transition metals or let us say this refractory niobium, zirconium or hafnium, and boron and copper. So, a typical composition is like 88% iron, zirconium is 7, boron 4 and copper. So, the microstructure here also we have alpha iron grains embedded in a amorphous matrix, and these are prepared by the same method that I have explained for the fine met series by annealing of the amorphous precursors. So, higher content of iron in the alloy composition exhibit a higher saturation magnetization and lower permeability. The reason is simple, because I increase the alpha iron phase, and this alpha iron phase in a higher resolution TEM image, you can see that this is a glassy matrix or amorphous matrix, and here is the crystalline particle of 5 to 10 nanometer diameter, where the distribution of the particles is one of the very important parameter, so that we can homogeneously disperse this iron alpha iron phase. So, here also this is another microstructure with a nanocrystalline phase. You can see the closed ring in the selected area diffraction. So, here also this is another alloy with molybdenum present. In case of zirconium, the molybdenum is added, where copper and boron both are present. The material was annealed at 550 degree centigrade to achieve such kind of alpha iron precipitate. So, this is a TEM image that shows the homogeneous distribution of such kind of alpha iron phases that assist on the development of the soft magnetic properties. So, these are couple of important microstructural aspect, and the further addition of cobalt in iron or replacement of iron with cobalt is also another very important aspect of developing heat pump series of alloy that can be used above 900 degree centigrade. So, magnetic properties are present there. So, please have a look at there. So, this is iron, cobalt, manganese metal, which is the metalloid like niobium, zirconium and hafnium in a heat pump series of alloy. So, just as a comparison, so here is the heat pump series of alloy where cobalt is added, and this is the Nano Perm. So, you see the magnetization value is definitely higher. So, we can achieve our desired properties compared to Nano Perm, as well as the change of the magnetic properties up to such a high temperature does not influence too much. So, we can maintain such a high magnetization, and when we are close to the TC value, so this is significantly higher, around 200 degree centigrade higher than the Nano Perm alloy. So, improve high saturation magnetization and better high temperature magnetic properties that can be achieved compared to the fine met or Nano Perm families. So, one important aspect of addition of copper, not only to improve let us say the glass forming ability of the alloy, but without copper and with copper, I show you two different microstructure, where without addition of copper you can see that the nanoparticles are clustered together, that cannot give us a better properties. Only when these nanoparticles are distributed in the matrix in a more homogeneous fashion, that can only improve the properties, okay? Because these are the hard magnetic particles of alpha iron that are act or assist in case of exchange coupling mechanism. So, the effect of copper addition is basically two ways that form a cluster that enhance nucleation of this iron cobalt nanoparticles. So, here I have alpha iron cobalt nanoparticle and also the uniformity of the distribution of the nanocrystallinity in the microstructure could be achieved by addition of only 1%, 1 atomic percent of the copper. So, these are some of the very interesting microstructural tuning as a metallurgist for the development of the soft magnetic alloys. So, if I like to summarize all these different alloy addition, we can think about that addition of silicon, let us say boron, copper or niobium and zirconium, they have the silicon and boron are added to improve the glass forming ability as I said. So, the glass forming ability is important because we have to produce a bulk material with a very good glass forming ability by choosing appropriate or optimization of the composition, and then we have to anneal those precursors, so that we get a uniform distribution of the alpha iron or alpha iron cobalt particles. So, the advantage here that improving high temperature magnetic properties and the disadvantage here by silicon and boron, that is the lower BS value, and that is why we have replaced silicon with iron cobalt system actually. So, in case of copper, we copper act as a grain refiner, they act as a seed for nucleation of the alpha iron, as well as it basically assist a homogeneous distribution of the nanocrystals. Now, niobium also act as a grain size control and also the zirconium, whereas we can think about some sort of nitrogen doping or let us say hydrogen doping and some germanium, tungsten, they can be used for further improvement of the glass forming ability and so on. So, there are various role of these quinary or quaternary alloy system that you have seen to produce the most important these iron based amorphous nanocrystalline alloys. But so far whatever we have discussed, we have seen that these are mostly iron rich or iron cobalt rich composition to get a better soft magnetic material. Now, the processing method for producing these amorphous precursors are mostly lying with the rapid solidification technique. The rapid solidification technique where we take a wheel that is made of copper and we pour the liquid metal into it, okay, let us say for a given temperature, and then the rebonds are produced. Okay. So, the liquid comes and then solidifies and the wheel rotate and continuously rebonds are produced. Okay. So, this can be done by some splat quenching or melt spinning, and this is a typical melt spinning apparatus that I have shown you. So, we can achieve let us say greater than 10 to the power 4, let us say 10 to the power 6 Kelvin per second. So, this is followed by some controlled annealing treatment. Now, we can also process by some powder metallurgy technique, that is consolidation of very fine powders. So, here magnetic nanocrystal that may be synthesized as freestanding powder and nano encapsulate that for further compaction to obtain bulk alloy using carbon arc or let us say the plasma torch or let us say the gas atomization synthesis. Okay. We will discuss this processing technique in the next week, do not worry. However, the crystallization of the amorphous precursors is also important. So, we may consolidate a powder and during consolidation itself we have annealed the powder, so that we can produce the desired microstructure, or maybe we have rapidly solidified such kind of ribbon and we get such a amorphous structure where there is no crystallinity at all and atoms are randomly arranged. So, we need to anneal it and to form some nano clusters of alpha iron phase in the microstructure, and that requires some controlled crystallization treatment. So, these are very important aspects of processing of the soft magnetic material, and we can think about the improvement of the processing technique by changing of the CCT or TTT curve. Okay. That we have also explained during the glass forming ability improvement. So, I have a liquid and then for a particular given composition that I have designed, I have a CCT curve like that. So, in that case I need a larger cooling rate to achieve this amorphous or glassy phase. But if I add some other alloying element and somehow if I can move this CCT curve to the right hand side in the time scale, then at a lower cooling rate means more bulk sample can be produced, and that is the advantage. So, the larger the time gap we get for processing a amorphous material is a beneficial effect. Now, the question will arise whether how finer microstructure is desired in a soft magnet. Could we make the nanocrystal of alpha iron more and more fine, means like 10 nanometer, 2 nanometer, or it is not desired. So, the coercivity value, which is a very important characteristic for a soft magnetic phase, I have plotted here with the grain size. Okay. So, in a grain size of 1 millimeter or let us say 10 micrometer or 100 micrometer, these are the alloy, that is iron nickel alloy called as Perm alloy. Okay. So, these are iron nickel alloy, or let us say some silicon steels, okay. They have such kind of grain sizes. Here the domain size, domain wall thickness, that is called the sigma wall, this has a smaller value than the grain size, means there are multiple domain in the grain, but if I keep on decreasing the grain size, then it goes to almost higher than 10 to the power 3 ampere per meter. So, we are reaching to the hard magnet size actually, and then if I further decrease the grain size to a 10 nanometer scale or 100 nanometer scale, where we have basically this boundary. So, in case of amorphous or nanocrystalline magnet, I reach to a certain microstructure length scale where the grain size is smaller than the domain wall thickness. So, it basically says that I can further decrease the coercivity value by producing this kind of amorphous magnet and producing some nanocrystal in the amorphous magnet by controlled annealing treatment, and that will be a better soft magnetic material. So, we have a crossover between these two different kind of length scale in terms of grain size. We will continue this discussion in the next class in detail. So, for today we close our discussion and thank you very much.